Good morning. It's so good to be back, and seems like it was only yesterday that we were here, but it's going to be a long time before November, so we got to get everything in that we can today. So I want to start out with some acknowledgments. Of course, Derek at Essential Depot has been a great supporter of our work. Mike Lawson of Columbus Foods was an early supporter and a very good supporter. Hampton-Sydney College, where I teach, has been very good at tolerating a nut job like me. And each semester I have some students to work on projects. This semester I've got Andrew Fazette, Matthew Chapman, Jefferson Thompson, and most of the work I'll be talking about today was done by Mitch Owens. So I'm going to work in two parts. First, how many of you know how to calculate saponification values? All right, so why not? I think most people are terrified of the math. Am I right? Yes. So I'm going to walk you through that. And even if you use a Lye calculator, wouldn't it be nice to know what the Lye calculator is doing? And so, and what do you do if you've got something that isn't in the Lye calculator? So we'll be talking about that this morning. Second part, we'll be talking about what happens when Lye goes bad. Does it have a shelf life, and what can go wrong with it? How can you find out what went wrong with it, and what can you do with Lye that's gone bad? Anybody interested in knowing about that? Yes. Okay, we'll talk about that this afternoon. But first, I've got some sodium hydroxide here, and we're going to weigh some out. And I want you to record the answer for me, and we're going to check it this afternoon. So the cup weighs 2.59 grams. You can write that on your slides. I've got some fresh out of the bottle sodium hydroxide from a little place called Essential Depot. And it now weighs 13.74 grams. And I'm not going to, say it again? Including the cup. Because we're going to weigh it later, and we're not going to be able to take the cup away. That would be pretty messy. So right now, 13.76 grams. And I'm just going to leave this out where it won't be disturbed. I'll put it somewhere later. And we're going to check its weight this afternoon and see if the weight has changed over the course of the day.
What did you weigh it on your phone?
Well, I'm going to be talking about that. I don't know if I'll get to it this morning, but certainly this afternoon I'll be talking about that little gemstone there.
Wow.
So, some of you will be bored by the next 4 minutes. You can go to sleep because it's review, but we've got some new people here, so I want to talk about oil and water. We know oil and water don't mix, and some of you can come up and give the speech that I'm about to give. It's about nerds and cheerleaders. So tell me about nerds and cheerleaders. What's going on there?
They want to be friends, but they just don't know each other that well.
And what's the major point? The major point is not that nerds hate cheerleaders. It's not that cheerleaders hate nerds. It's that cheerleaders like cheerleaders more than they like nerds, and that's all that's necessary. In high school cafeterias across the universe, cheerleaders are sitting together and nerds are sitting together. The cheerleaders are sitting together because they like other cheerleaders more than they like nerds. The nerds are sitting together because no place left to sit. So oil and water are like that. The oil is like the nerds and the water is like cheerleaders. Water molecules are attracted to one another more than they're attracted to oil. So water tends to congregate together, and the oil goes wherever the water isn't. We say that it's hydrophobic, but it doesn't really mean that it fears water. All right, so this is what the kind of oil that we use is a triacylglyceride. It's got 4 parts to it. This is what oil looks like before it's turned into soap. we've added some hydroxide ion. Those are the three little things. And you see that the oil molecule is like a hand with three fingers on it. And when the hydroxide attacks that molecule, dink, one comes off, and that little finger that's just been amputated is a soap molecule. I got two more hydroxides left. Think, there it goes again, and I have two soap molecules. Think, and now finally I've got three soap molecules and what that thing in the middle, the knuckle where the fingers used to be attached, is glycerin. Okay, so that's the basic chemistry of what's going on whenever you mix oil with lye. All right, soap is a nerdy cheerleader. It's a Siamese twin. Part of it is a nerd and part of it is cheerleader. Part of it is hydrophobic, part of it is hydrophilic. The hydrophilic part will be congregated with water molecules. So in water, the polar head group, the hydrophilic head group, will be attracted to water molecules, and the hydrophobic tail will be, I won't even say attracted to oil, it's just that it goes wherever water isn't like all the other oil does. And so this forms a bridge between oily things and watery things, and when we're using soap, mostly what we're trying to get rid of is oily things. If they weren't oily, we'd just wash our hands with water and be done with it. All right, this is an example of a fatty acid. This is stearic acid. And on the top, I've shown you a molecular structure of it. And the color coding here is that green is hydrophobic or hydrophilic? It's hydrophobic. That's the hydrophobic tail. And the red and white atoms at the head are the hydrophilic part. Those are the parts that are attracted to water molecules. Underneath, there's a stick structure. It's hard, you know, you're sitting around talking at the table. You can't draw a figure like the molecular graphic at the top. So we just kind of scribble things down. We draw the hydrophobic tail just as a squiggly line. And at the head, we see two oxygen atoms. The two oxygen atoms is what's going to form the hydrophilic head. And now we can talk about, just drawing on napkins, we can talk about the chemistry of soap. This is a fatty acid, not a soap. What's the difference between the two? Remember from last time? It's just one hydrogen atom different. So the fatty acid has a hydrogen stuck to the hydrophilic head, and a soap molecule doesn't. This hydrogen's been replaced by sodium in that case. This is oleic acid, and oleic acid is a fatty acid that's unsaturated. It doesn't have the maximum amount of hydrogen that it could have, and that puts a kink right in the middle of the molecule, and the kink is what makes liquid oils liquid, whereas solid oils are solid. Most of your saturated fats are solid at room temperature. Most of your unsaturated fats are liquid at room temperature. Here are the saturated fatty acids that we deal with at the, most frequently. At the top is lauric acid. That's the shortest of them. Then myristic acid, palmitic acid, and stearic acid. And this is a lot to see on one slide, but all I want you to do is get used to seeing that squiggly line, stick structure. And if you look, there's something called the molecular weight there. And molecular weight tells you how many grams a mole of molecules weighs. And if you're scared of the word mole, don't worry about it. We're going to get to that. But they're proportional. So of these fatty acids, which one weighs the most? Stearic acid weighs the most, and which one weighs the least? Why does it weigh the least? It's shorter. That's the only difference. So we got fatty acids that are relatively short, fatty acids that are relatively long. Here are the unsaturated fatty acids. And the oleic acid has one kink in it. Linoleic acid has two kinks in it. Linolenic acid has three kinks in it. And there's another kind of weird one. It's the only one like it. It's ricinoleic acid. And it's got an extra OH group right smack in the middle of the molecule. If you look at the weights, let's just remember the weights of the previous slide. What's the heaviest of these fatty acids, saturated fatty acids? Stearic, and just let's stick a number in our head. What is the weight of that stearic acid? Because just remember that for like 12 seconds and compare that weight to these weights. These are the unsaturated fatty acids. They're really, really close. And why are they really, really close? Because they are the same length. They're all 18 carbon atoms long. So the unsaturated fatty acids are about as heavy as the heaviest of the unsaturated fatty acids. All right, we got a new word for you, and it's a fun word, and you can trot it out and impress all your friends. It's called stoichiometry. Say it with me. Stoichiometry. It's a big, long word, but it has a very simple meaning. All it means is how much of this goes with a given amount of that. You got a cake recipe. How many eggs go into a cake recipe? And it depends on how big the cake is, right? It depends how big the cake is. So you have to say, well, I'm making a single layer cake this big. How many eggs? 2 eggs. If I'm making a 3-layer cake, how many eggs? 6 eggs. That's stoichiometry. So it's a fun word to say. We're going to apply stoichiometry to soap. How much sodium hydroxide is needed to react completely with a given amount of oil? That's the fundamental stoichiometric question. So how many molecules of sodium hydroxide are needed for each molecule of oil? If you remember our graphic, how many fingers were on the hand? 3 fingers. How many hydroxides did we need? One for each finger. So for each molecule of oil, how many molecules of sodium hydroxide do I need? 3. I need 3 molecules of sodium hydroxide for each molecule of oil. Now here is a more difficult question. How many dozen sodium hydroxide molecules do I need for each dozen molecules of oil? Wow, you did that really quick. I didn't even see anybody whip out a calculator. 3 dozen sodium hydroxides to react with 1 dozen molecules of oil. How many gross of sodium hydroxide do I need to go with a gross of oil? 3. Wow, you guys are really sharp. Okay, now here's the hardest of them all. How many moles of sodium hydroxide do I need to go with a mole of oil? 3. Now, you don't even know what a mole is. And you know the right answer already. You don't even have to know. If you want to know, I'm about to tell you. So how much is a dozen? 12. How much is a gross? 144. A mole is 1.23 times 10 with 22 zeros on the end of it. That is a big number. But the good news is it doesn't even matter. All that matters is we're using the same unit for the sodium hydroxide as we are for the oil. It's just a number. And it's a 3-to-1 ratio, however big or however small that number is. Are you still scared? Good. Maybe a little. If you're honest, you're still a little scared. All right, we need to talk about atomic weights now. How much does a mole of atoms weigh? And the weight of a mole of atoms depends on what the atom is. A mole of hydrogen weighs 1 gram. A mole of carbon weighs 12, a mole of oxygen weighs 16, and a mole of sodium weighs 23, and a mole of potassium weighs 39. So where did I get these? You've all seen it probably. It's on a periodic table. There are 2 little numbers for each element, and this is one of them. I don't even care if you know what the other one is. This tells me for that ginormous number of atoms or molecules, how much does that ginormous number weigh? And it depends on which atom I'm talking about. If I'm talking about molecules, all I have to do is add up the atomic weights. So for sodium hydroxide, it's 23. That's what? 23 is which element? That's the sodium, and 16 is the oxygen, and 1 is the hydrogen. If I add those up, 23 and 16 and 1 adds up to 40. And 40 is the molecular weight of sodium hydroxide. Potassium hydroxide, almost the same material, except it's got a potassium instead of a sodium. Sodium weighs 23, but potassium weighs 39. If I had 39 and 16 and 1, I get 56. So that's why when you're making soap, it matters to you whether you're using sodium hydroxide or potassium hydroxide. The molecular weights are different. All right. Now we need the molecular weight of this oil molecule. All right, let's get busy. You've got a little graphic there. Count up all the carbon atoms. Those are the green ones, and multiply them by 12. And each one is surrounded by hydrogen atoms. Add those all up. Those are all multiplied by 1. I got some oxygen atoms there. There are 6 oxygen atoms in the molecule. That's each one times 16. And, well, maybe I'm not going to do that just by counting them up, but I could. If I did glyceryl trilaurate, that's the glycerin with 3 lauric acid molecules attached to it, would be 638.95 grams. Glyceryl tripalmitate would be 807 grams. Why does glyceryl tripalmitate weigh more than glyceryl trilaurate? Yeah, exactly. Because the palmitic acid is 16 carbon atoms long, but the lauric acid is only 12 carbon atoms long, and each carbon atom has some weight. So we're going to remember those numbers. All right, how many moles are in a kilogram of oil? And I'm going to give you a little toy problem first. Which has more in it? If I have a pound of grapes or a pound of apples, which one has more grapes or more apples? In a pound of grapes, there are more or less grapes than there are apples in a pound of apples. Why? Wow, you guys are really... how in the world are you doing that? Because grapes are smaller than apples. Okay, so how would you do that mathematically? You would divide one by the other. We're going to take 1,000 grams and divide it by 638.95. 638.95 is what? It's the... Say the name with me. It's the molecular weight of glyceryl trilaurate. So I divide the weight that I'm interested in by the molecular weight. That tells me how many moles. In 1,000 grams of glyceryl trilaurate, I've got 1.56 moles. Now that's a lot easier to understand than 6.23 times 10 to the 23rd, right? Okay, so glyceryl tripalmitate, same kilogram, how many moles? 1.24. Why are there only 1.24? Because they're bigger molecules, and in 1,000 grams of oil, there are going to be fewer molecules than there would be if the molecule had been smaller. All right, so now I know that. How many moles of KOH do I need to react with that kilogram of oil? Where glyceryl trilaurate had 1.56 moles, and how many moles of KOH do I need for each mole? 3 to 1. 3 times 1.56 is 4.68. If it were glyceryl tripalmitate, it'd be 1.24 times 3 is 3.72. The numbers are different because the molecules are a different size. Which one needs more KOH, the little molecule or the big molecule? No, so for each molecule. Now for 1,000 grams. For 1,000 grams, which one needs more? The little molecule needs more grams of KOH per 1,000 grams of oil because it's smaller. All right, how many grams of KOH are needed for a kilogram of oil? Well, now I have to multiply by the molecular weight. Before I had the number of moles of KOH. Now I need the number of grams of KOH, because you know what? There's no such thing as a molometer. I can't go out, Google molometer. You won't find it anywhere. Nobody makes such a thing that just measures out moles. We weigh things out on a scale or a balance, and so we need to convert it to weight. 1 mole of KOH weighs 56 grams, so for glyceryl trilaurate, I need 262, I don't have my glasses on, but for glyceryl tripalmitate, I only need 208. Do those numbers look at all, maybe even possibly sort of in any remote way familiar to you? Ah, well, we'll see. How many grams of sodium hydroxide do I need? Well, it's exactly the same number of moles, because it doesn't matter, it's the hydroxide that's reacting. Doesn't matter if it's KOH or NaOH, but NaOH weighs more or less than KOH. It weighs less, so when I multiply it out, I get 187 and 149. Do those numbers look in any way possibly familiar to you?
Yes,
What are they?
the number from up above.
All right, so hopefully you will say, hopefully in a few minutes you're going to say, oh. Okay, now hear it all in one slide. This is the most terrifying slide of my entire presentation. This is where the math is. But it's exactly the same math that we've just done. It's just done all at once. I ask how many grams of KOH are needed for 1,000 grams of glyceryl trilaurate. 638.95 is the, say it, mole. This is the molecular weight of glyceryl trilaurate. That converts it to moles. I got a 3-to-1 ratio of KOH to glyceryl trilaurate, and each mole of KOH weighs 56.11. That gets it all done in one giant fell swoop. I get 263. And I'm going to use a word here, parts per thousand. Parts per thousand means how many parts, how many grams per 1,000 grams. You're used to something called percent. What's percent? Percent is parts per 100. This parts per 1,000, it's just got one more digit on it. This is for sodium hydroxide. I get 188 parts per 1,000. In practice, we don't know the molecular weights. We would be done if we could just kind of look up what's the molecular weight of coconut oil, what's the molecular weight of palm oil, but these things are not pure compounds. They're mixtures of all kinds of different fatty molecules. And so in practice, what we have to do is measure how much sodium or potassium hydroxide does it take to completely saponify 1 gram of oil. That's listed in a table of saponification values. Scientific soap making has a table in the back, but it's different from the tables from most of your soap making books in that it doesn't just have one number. It has a range of numbers. So glyceryl trilaurate was 187 parts per 1,000. In decimal, that's 0.187. Glyceryl tripalmitate was 149. That's decimal 1.149. Coconut oil is a range of 176 to 189, or 0.176 to 0.189. And palm oil is 0.135 to 0.149. Now do you see any similarities? They're SAP values, yeah. Compare the SAP value of glyceryl trilaurate to these real-world oils. Which one is it most like? It's most like coconut oil. That isn't an accident. It's because coconut oil contains mostly glyceryl trilaurate in addition to other fats. And which one is glyceryl tripalmitate most similar to? It's most, I wonder how they came up with the name palmitic acid. It's because they isolated it first from palm oil. Now, I said, in a minute you'll go, oh, and you just did. Okay, so these numbers start to mean something other than just numbers in a book. If you look at sap values for coconut oil, how come the sap value of coconut oil is bigger than the sap value for palm oil? Because which molecules are bigger? The palm oil molecules are bigger than the coconut oil molecules, and therefore the sap value for, oh, it's exactly backwards, isn't it? The sap value for the coconut oil is bigger than the sap value for the palm oil, because there are more molecules in a given weight of coconut oil than there are molecules in a given weight of palm oil. That's what it was for KOH. Here is the same numbers. There we go. There's sodium hydroxide. Okay, so Lye calculators use an average value. That's why you only get one number. When you look up coconut oil in a typical soap making book, it'll tell you what the saponification value is. Sorry, life isn't that simple. Coconut oil changes from one supplier to another. Where was the coconut grown? What was the season of it? It changes, and so we get a range of saponification values, not a single number. So most soap making books will say, take the average number. They don't even tell you that it's an average number usually. Take the average number, and now they recognize that some coconut oil may have a lower or a higher saponification value. What's the one thing that you want to avoid? Too much lye. We don't want to have too much lye, so they say, you know, take the average value and then discount it. What do we mean by that? Use less. You're going to calculate how much you need, and then you're going to use less than that. I take a slightly different approach. I say, you know what? There is a lower limit. Let's just use that number. Then you're guaranteed that any coconut oil you find is not going to have a higher sap value than that, and that way you're guaranteed not to have an over-alkaline soap. It doesn't matter which way you do it. You can do it both ways, but that's the way that I prefer, because it's a guaranteed result rather than just going on an average. So now we have 4 different oils. We have coconut oil, palm oil, olive oil, and castor oil. And here are the sap values for each one. How many pounds of sodium hydroxide? Oh, that's what's going on. I have to remember what's going on here. So this is grams. This is pounds. How many pounds of sodium hydroxide are needed for a pound of oil? That's moles. Just look at the slide. Oh, look, for coconut oil, it's 0.176. For palm oil, it's 0.135. And that's in pounds, pounds per pounds. How many grams? Coconut oil, 280 times 0.176 gives me 49.28 grams of sodium hydroxide. It's simply multiplying however much weight of coconut oil you have by the saponification value as a decimal. 280 grams requires 49.28 grams of sodium hydroxide. For palm oil, I want 280 grams of palm oil. I multiply by 0.135. Where did I get 0.135? It's the sap value for palm oil. Multiply those two together, I get 37.80. Here's the trick question. If I need 49.28 grams for the coconut oil and I need 37.8 grams for the palm oil, how much total do I need? I just add them up. I need 87.90 grams total. All right. Now I'm going to add 390 grams of olive oil. Well, that's 390 grams times 0.131. What is that? Sap value for olive oil, I need 51.09 grams for the olive oil, and for the castor oil, 50 grams times 0.125 tells me how many grams of sodium hydroxide I need for the castor oil. How much total do I need? It's not brain surgery. I just add them up. I needed this much for this one and this much for that one, and the total is just adding them up. 144.42 grams of sodium hydroxide. Wait a minute. 280 grams of coconut oil and 280 grams of palm oil and 390 grams of olive oil and 50 grams of castor oil adds up to 1,000 grams of oil. Now I ask, how many grams of NaOH do I need for 1,000 grams of this mixed oil? 144. 144 is the saponification value for this oil mixture. If you're master batching, you can calculate the sap value not for the individual oils, but for the master batch of oil that you've mixed up. All right, I call this Duck Bar's Delight. That's the name of the oil mixture. And if I have 16 ounces, how many ounces of sodium hydroxide do I need? Oh, I just multiply 16 by 0.144. That's the sap value for the mixed oil, 2.3 ounces. All right, so here's a practice problem for you. Your formula calls for 56 ounces of coconut oil, 56 ounces of palm oil, 78 ounces of olive oil, and 10 ounces of castor oil. How many ounces of sodium hydroxide are needed? And this is not a rhetorical question. You now have some work to do. You can work in pairs, and I want an answer in the next. Remember what it's written on the previous slide. 0.144 is the value for the mixed oil. Now, about 3 of you are actually taking me seriously and working it out, but I'm just going to stand here until you're done. So if you want to check your email or whatever it is that you've got going on. Okay, you ready? You're exactly right. Okay, let's look. Let me just think about this for a second. I had 280 grams and 280 grams and 390 grams and 50 grams. Look at these numbers. 56 ounces, 56 ounces, 78 ounces, 10 ounces. The ratios are exactly the same, except this is like twice as much, and it's in ounces instead of grams. It's twice as much. Oh, 14.4 times 2 is 28.8. Oops. All right, so that was the right answer. And it doesn't matter now. It doesn't matter whether you want to work in grams. It doesn't matter whether you work in ounces. It doesn't matter whether you work in pounds. The thing that you want to do is use the same unit throughout. If you do, the calculation is exactly the same. There's only one thing you want to avoid. You don't want to work in pounds and ounces. Then you got to convert. You're working ounces or working pounds. So if you make that choice, the calculation is as easy as what we've done so far. All right, I have 15 minutes. This is where I intended to get by the end of the hour, but I want to leave lots of time this afternoon to actually roll up our sleeves and get our hands dirty. So I'm going to march ahead and give you the kind of the intro to what we'll be doing this afternoon. When lye goes bad. So I'm going to, in the world, when you go out in the world, people will use 3 terms synonymously. They'll talk about lye. When they're talking about lye, what do they usually mean? Sodium hydroxide, or kind of the old word for it is caustic soda. I'm going to use the 3 words not synonymously. And I don't really want you to go out in the world and tell people they're wrong to use them synonymously. It's just that we have three different things, and I want to have words for them so we can talk about them. So when I talk about caustic soda, even though this bottle is labeled sodium hydroxide, I'm going to refer to it as caustic soda. It's the white stuff in the bottle that you got from somebody who sells you caustic soda. What chemical is in caustic soda? Sodium hydroxide. So I'm going to make a distinction between sodium hydroxide, the chemical, and caustic soda, the white stuff in the bottle. And furthermore, when I dissolve this white stuff in water, I'm going to call that lye. And that kind of follows the original meanings of these words. It's not that they were ever used that precisely, but I want to now draw a distinction between caustic soda, the white stuff in the bottle, and sodium hydroxide, the stuff that you need to make soap. Okay, so when you leave this afternoon, I don't care if you use the word synonymously, but at least for the purposes of our talk, I'm going to use them very specifically. This is the Certificate of Analysis of Essential Depots caustic soda. And I know you can't read that, so I blew it up. So we see a bunch of numbers in here, and at the top is Fe. Fe. Anybody know what that's the symbol for? Iron. This is how much iron is present. The unit is parts per million. So this stuff is allowed to have up to 15 parts per million iron. Why is it allowed to have any iron? This is food grade, and it's allowed to have 15 parts per million iron. How much is a part per million? Well, remember we talked parts per thousand and parts per hundred. Parts per million is really tiny. The number isn't zero because you know what? If you aren't going to find anybody anywhere in the universe to sell you something with 0 parts per million iron. They might get it down to 1, and if you wanted 1 part per million iron, you would be paying a lot of money, because to get that last little bit of iron out is very expensive. How about mercury? You would like to have mercury in your soap? No. Well, we're allowed to have up to 0.1 parts per million mercury in food-grade sodium hydroxide, because if you wanted less than that, you wouldn't be able to afford that sodium hydroxide. So these are upper limits. Sodium carbonate, 1.6, and what's the value? Percent, up to, what is it? 1.6% by weight. Why don't they have that to be less? And notice it's a bigger number, right? A percent is a lot bigger than a parts per million. Why do we allow so much sodium carbonate in here? We're going to find out. I'm not going to spill the beans there. Sodium oxide is what you would get if you removed all the water from sodium hydroxide. NaOH, well, you know it's got an O and an H in it. If you took those out and just had sodium hydroxide, up to 100% of that. Sodium chloride, up to 2.3%. So you see what these are, and then the ones at the bottom, these are meshes. So this stuff is of a consistent particle size. They run it through a screen, and this says that you 100% will pass through a, I can't read that, I think it's 16 mesh screen, but only 2% of it will go through. Is that a 60 mesh screen? So it means that the particles are of a consistent size. Food grade is different because, you know, if it's food grade, what if it weren't food grade? How much mercury would I allow in a non-food grade sodium hydroxide? Probably more, right? And it would be more expensive or less? It would be less expensive. All right, the certificate of analysis tells you the information about the quality of the product as measured by the manufacturer. The most important contaminants, though, are not even listed. The most important contaminant in sodium hydroxide isn't even on the certificate of analysis because they just can't control it that well. It's water. Now, I can avoid adding water to sodium hydroxide, but I can't absorb sodium hydroxide from getting water. Where is it going to get it? From the air. It gets it right from the air, and we poured some in a cup, and we're going to check it. Is it on the back there?
It's right, no, on the table.
It's on the table. It probably hasn't picked up any weight yet, but let's check it out. What was the number that it weighed before?
13.76 grams.
The weight now is 13.85 grams. What was it before? 1376. Already it's picked up some water. So we're going to check, we're going to leave it there all day.
Was it 1384?
1380. I have a mind like a sieve. They could pass this stuff through my brain and it would come out a consistent mesh size. 13.84, 13.85. It's the last digit will jump around a little bit. 13.85 is what it's right now. So they can't control that. The manufacturer has some control of the product as it leaves their factory. But then it comes here. And they buy it in giant lots of sodium hydroxide, and then they break it down into smaller bottles. And you know what? In order to do that, they have to open the bottle, right? And, Florida. Probably not much humidity here, I don't think. No, probably not, probably not. So some moisture is going to be picked up as they're breaking it down into smaller packages. And now Derek is doing his best to get you nice dry sodium hydroxide, but then you get it to your shop. And I wonder what fraction of soap shops are in the basement.
We don't have basements in Florida.
Oh, not in Florida. No, you don't need a basement. All you need is the atmosphere. But a lot of soap shops are humid, and so every time you open the bottle, it picks up moisture from the air, and it picks up one more thing from the air. It picks up carbon dioxide. Carbon dioxide is an acid. Sodium hydroxide is a base. So you're sitting there in the soap shop, you're working away, you're huffing and puffing, you're exhaling carbon dioxide, and you left the sodium hydroxide open. It's not a catastrophe. I don't want you to be paranoid that you have to put the top on, 12 microseconds after you opened it. But the longer that bottle is open, the more moisture and carbon dioxide it picks up from the air. Okay, so how many of you think that you've had a bad batch of sodium hydroxide before? You don't hear about it a lot, but you hear it about it occasionally. I wonder what happens when I make soap with bad sodium hydroxide. Normally we make Duck Bars Delight using a master batched oil, 50% lye, bar of soap can be made with 100 grams of oil, 28.8, there's that number again, 28.8 grams of lye, 14.4 grams of water. That's equivalent to 14.4 grams of sodium hydroxide and 28.8 grams of water. However, if our caustic soda has absorbed atmospheric moisture, 14.4 grams of caustic soda will contain less than 14.4 grams of sodium hydroxide. And that's the fundamental problem. If we had 95% sodium hydroxide, that is, it had picked up 5% of its weight in moisture, then 14.4 grams of caustic soda would actually contain only 13.68 grams of sodium hydroxide. It would have an extra 0.72 grams of water, and we can simulate this. I tell people, I make bad soap on purpose one bar at a time, to answer questions. And that's exactly what we did. So at 100% purity, I would use 28.8 grams of lye. Remember, lye is the solution, 50% solution. And here I've simulated what would happen if I had 95%, 90, 85, and 80% sodium hydroxide in my caustic soda. I've not given you numbers here for hardness because my student hadn't completed the experiment when I made up the slides. So I'm now going to give you those numbers. The 100% one you can write in had a hardness of 1.00. At 95%, it was 0.75 hardness. At 90%, it was 0.35 hardness. At 85%, it was 0.25 hardness. And at 80%, it was 0.20 hardness. 1/5 of the original hardness. And you say, hardness? How in the world are you going to calculate hardness? And I'm going to leave that for this afternoon. Okay, thank you very much, and look forward to following up this afternoon.